Okay, tonight's gonna be a little bit different. So I put together an actual basically playlist of things to go see tonight, and I just wanted to try it out with you and see how it works. If it works well, then I'll do this every stream. But now, last night was a record-breaking stream. I went over 5 hours. And I didn't even notice how fast the time went. So I can't do that again tonight, but it should be pretty interesting. So we'll try it. We'll try to see how far we can go tonight. The temperature's a little bit warmer, and we also have a special guest that's going to be joining us here in a moment. And I'll tell you who that is in a second. And you'll be able to hear it, most likely. So tonight we're going to do some really interesting, we're going to see some really interesting sights tonight. And I'm actually looking at my playlist right now, things I want to do. I'll show you in a second. Hold on. Little housekeeping here. Let me just get this housekeeping done. There we go. This is better, I think. Alright, so I expect that you are there.
Yeah, we're jamming.
Hey, ladies and gentlemen, it's Keith Ickes from P&K Space Imaging.
Yeah, I was out actually hanging out with Bill a lot last night. I think we did 4 hours over there last night.
Wow, I did 5 last night here.
Yeah, it's because you're crazy.
I am.
That's a pretty long time to be out there in the dome. Wasn't it cold up there last night?
It was. It was very cold. Very, very cold. Actually, I had to stop because I was cold, but I just couldn't help it because I was looking at the Orion Nebula. Did you see the Orion Nebula photos at all?
Yeah, I was actually looking through the photos earlier.
Wow. They were just beautiful. Absolutely beautiful. I couldn't believe how nice they looked. And I took someone that was like right on the horizon, you know, and then wow, you know, it's like, look at this shit. Oops.
Yeah, you would almost think you were a professional astronomer or something.
Or something, you know.
But yeah, beautiful pictures. I was looking at them on Facebook.
Yeah, it was just stunning. I just couldn't believe it.
I'm not sure what's happening with Astro Imaging Live, the Facebook page, but I've been adding people, probably at least 3 people every hour.
Nice.
for the last 2 or 3 days. I've just been getting constant things of people wanting to join that. So.
Well, that's good because what I've been doing is I've been doing some shows, and I would send them all my bio information, and in it, it has Astro Imaging Live as like a conglomeration of all the best of the astronomy streams.
Oh.
And so
that might be what it is. And I noticed a lot of them
that's
are
part
coming
of it
from
for
Texas.
sure. Oh, interesting, because the show I did was in Miami. Yeah.
Yeah.
And they got me. They didn't even talk about it on the air. I mean, but
No.
we mentioned it on the air briefly, but I did mention P&K Space Imaging. What was I on? I was on a show last night? No, night before. Last night I was here, and I mentioned that you were out there, that we're out there, Bill New York Skywatcher as well. So I imagine that there's got to be some kind of effect going on there, you know?
It's got to be because, as I said, I mean, I've been getting requests left and right to join the Facebook page, which I'm thinking about stealing your photos and putting them there as well.
Go right ahead. I think
or
you
maybe
should.
Sharing your site on that page.
You can bring the do both. I mean, if you want to, but I think it's important to dress it up, make it look nice. You know, it's great. I'm looking forward to when it goes live in a very big way. Because right now, I changed the name of my stream now for the current date. And when I do that...
Finally.
When I do that, it makes the link different.
Yeah.
And it means we have to have some kind of an auto updater. Now, folks, I don't know, you guys listening, I don't know if you are aware of, you probably are, astroimaginglive.com. But astroimaginglive.com is the site where it actually started thanks to Bill, New York Skywatcher. He actually had the site before, and he then basically donated his time and his space on the site to give P&K and SkyTour LiveStream a home there.
Kind of to put us all under one roof.
Yeah, and that was very big of him to do that. So we can't forget that. So make sure you guys give a shout out to Bill at some point. And frequent his stream as well as, of course, Paul and Keith.
Who I should also mention was capturing some nice meteors.
I saw them, and last night here it was like, oh, I don't know, it was around 2:15 in the morning, and I was in the dome looking up, and I saw two beautiful meteors go over with beautiful green trains behind them. It was just stunning. Nice Orionids.
I do have a nice little announcement in case you're interested, Mark.
Please go for it.
If anybody wants that 12-inch Meade that Paul has, you can probably get it. I think he's putting it up on eBay because he just ordered another one.
What is going on with it?
He just ordered a Meade 12-inch 305 millimeter LX90.
Yeah.
Let me see the
ACF.
Let me see here.
Is it an ACF system?
UHTC high contrast coatings,
Okay,
Meade 12-inch 305 millimeter 3048 millimeter focal length. So. Yeah, I mean, he had more info. He sent me a whole bunch today.
Wow.
A whole bunch of texts. I didn't get them all at one time.
It's nice to only have one obsessive thing you do with your money.
Yeah, but he told the guy that he bought this one from that to keep an eye out and if he can get a 14-inch. The man's obsessed, I tell you.
You don't have to tell me. I mean, it's pretty obvious that the guy's obsessed. Let me tell you. I love it though. I think he's doing a great job. And for those of you who go to P&K Space Imaging, make sure you throw a few comments Paul's way and say, "What are you doing? Are you crazy? Are you out of your mind?" There's more telescopes in your building than there are people in that mall.
Yeah. Well, I figured I mentioned to you just
like
in
a
case you wanted
telescope store.
One for a portable.
Well, it's
a portable 12-inch.
Well, what you're suggesting is actually something I've been mulling over. You know how when we talked about the in that news conference about the gravity waves, they talked about the interferometer where they had a 1.2 or 2 kilometer or so leg on each side of the building, and those went out to the sensors that gathered the signals that came from these gravity waves, so they could detect gravity waves passing through the Earth. Well, that made me think, gee, what if there were two identical observatories with telescopes in them, and they were both synced, one slave to the other, so that when one looks at one thing in the sky, the other one's looking at the same thing, and they're just slaves.
You're talking about twinning them up.
Yes,
much.
And then if you twin them up like that, if you pair them like this, then on top of the UFOTOG 2, which is now the Aerial Anomaly Detection System, okay, ADS, now on top of that,
I like that name so much better, by the way.
It's going to get funding. That's the name that'll get funding, okay? You put UFO in something and they run away. And I talked to Doug about it, and those of you who know who Doug Trumbull is in the chat, in the chat. And basically, Doug and I have been building this system for about 3 years now, maybe a little longer. And I thought it was going to be ready 2.5 years ago. I thought it was going to be a very quick and easy thing to do. And the more I dove into it, I was a software developer for many, many years, 15 years. So I looked at it from that point of view, and I said, that won't be that bad. Well, it turns out it was that bad. So there's a lot more to do, and the problem is integrating all this disparate hardware that has to talk to each other. That's the only thing. So that's taken a long time, but this observatory that I'm in right now, that I'm banging the floor in, this observatory is testing the Aerial Anomaly Detection System gear. As we speak, I've got something mounted on here that I'm testing right now. And so I think it's important to understand that, well, this observatory actually serves a major purpose. Yes, it provides the SkyTour LiveStream with a home. It provides all of you with someplace to go on a night when you don't know quite what you want to do with yourselves. But it also gives everyone, and you'd agree, Keith, it gives everyone in front row seat to the developments in this project, because everybody believes in this project as we do. I mean, and we haven't asked anyone for money. We're not going down that path at this point. We're not pulling a Tom DeLonge type routine where we're gonna, try and start looking for money. But I did send a message to Tom DeLonge, and hopefully he'll respond with a positive response.
Well, how many of these do you want? Like, what is your goal to put out initially?
Well, I just want to get like 3 initially, just to be able to put the whole system to the test. They have to talk to each other, and then they have to send alerts through the GPS satellites. That stuff, that GPS satellite part, that works. That's already done. That works already. And because we're leveraging. So
you're not gonna put anything out until you have 3 of them, pretty much.
I'm sure that Doug could talk me out of that, but I would like to have 2 minimum, 3, ideally. Just one? Well, we're going to have just one for some period of time anyway, because we're going to be testing. But the thing is, when we create one, that unit is going to have to bounce against something. It's going to have to go against some other data. We're going to have to make sure that its data is valid. We can calibrate it till the cows come home and make sure that the readings we get from the system are right. But when we compare it against another system, okay, with the same sensor, perhaps the location is going to make the readings different. And that's when we'll discover, the magnetic field is, as we suspect, and this is an easy one because we know this is true, the magnetic field is actually different at each location. Not meaning it points north differently. I mean, it can point in wildly different directions.
Well, what's your goal of like the minimal space apart? Like, are you looking? Are you putting all 3 in the same state? Or are you looking to bounce them to, across, say, what's the ultimate goal, I should say?
Well, that's a great question, because looking at the interferometry, okay, when you look at that setup and how that works, all of those systems are just about a mile apart from each other. A little less, a little more in some cases, right? Virgo's a little different. But the thing is, we have 3 systems, 3 units that we want to put in a triangular equilateral triangle, so each side is the same length and the same angle. And we think that they'll be about a mile apart. Each leg will be a mile from the other. So, Unit A will be 1 mile from Unit B downrange, and Unit C the other way. This gives us enough wiggle room so that when we see something in the sky, if A and B see it, then we will be able to triangulate altitude, distance, and speed and all that, which we can't do from one setting. You have, each platter is going to have like 5 instruments, right? So we're going to get 5 readings from 5 different instrument sources on each platter. But if we only have 1, then we'll just get 5 readings, and that's better than only 1 shaky image, of course, or 1 shaky video, rather. But you know what? If the thing comes out to be, if it comes out to be something like, something that's moving through the sky and it suddenly makes a sharp right angle, you're going to wish you had the other data to be able to tell how fast it moved and how high up it was.
Right.
So, and
it's all
nice,
about triangulation.
Yes, and that's right. And that's why we call these the layout triads. We just lay them out in little triads. And the thing is, if we do have these laid out like that, 1 mile is the nominal distance that, for instance, can exclude local events. For instance, if it's an aircraft, it's going to very quickly move through the two sets of views, and we can triangulate it, all right? But we may not have to, because one of the things we're going to do is put what's called a transponder decoder on each platter, and that's a little tiny device that you can literally go and buy online right now, and you'll be able to decode the incoming ADS-B signals coming from the aircraft going over. Now, every modern aircraft has this on it. Military aircraft may or may not. So we will get, bogus returns on military aircraft, at least for a period of time. But then, over time, we'll be able to train the system to recognize the navigation lights, for instance. And that's down the line. That's an advanced thing, and that's when we have some programmers on staff that are going to be, hot shots and say, "Hey, can I tackle that blinking light problem?" And I'd say, "Have at it, man."
Well, isn't there like federal regulations about the blink patterns of planes?
That's my point. Yeah. Okay.
Yeah, so I mean, the data's probably out there.
Yeah. Well, the FAA.
Yeah.
And I pursued that actually, almost a year and a half ago to figure out what we're going to have to do for aircraft. And actually, aircraft are going to be the easiest thing to discern. Okay. Because unless a military craft is flying in a blackout mode, okay, it's still going to have navigation lights, even if it doesn't broadcast ADS-B data. And ADS-B data, for you guys in the audience that are listening, ADS-B data is the data that every single plane transmits, modern plane I should say, transmits. And this ADS-B data is something that when we look at the information coming from it, it tells us the altitude, the speed, actually even the origin and destination of the aircraft. So we can get everything. When you get what is it, FlightAware 24? No.
Flight Radar.
Yeah, Flight Radar 24. When you get that application, it's looking at the ADS-B data, not from your phone, but from a master server. Okay, and so we can also get that. If they can get it, we can get it too.
Nice.
So we can say, oh, there's going to be a plane coming through at this location at this bearing, so ignore this for the next 10 minutes. We can go that route as well, do preventative stuff. But I would rather let the units decide whether it's an aircraft or not, and let's see what it sends us and what it thinks it is.
I'll tell you what, that's kind of what Jello was doing last night. Like, Jello had something open where he was actually telling us, like, right before planes would show up, and he would tell us what the plane was.
Yeah.
And then next thing you know, here it comes through the screen.
Yeah, he's linked up to the ADS-B data. You can go to the website and put the map full screen on your computer and have fun for the night, and it's wonderful. I love it.
So what's on the agenda for tonight?
Well, tonight we're going to actually look at a bunch of things. This is the Omega Nebula right now. And the Omega Nebula is actually kind of one of my favorites. But after, I don't know if you saw the Andromeda Galaxy photos.
I did, and I was staring at it for a good 15 minutes.
Did you notice I actually did some additional processing on Andromeda, where I actually pulled out the detail of the dark lanes inside the core.
That's what I was looking at, because I was about to take that photo and then run it through the programs I have here and make it actually pop.
Well, you know what? If you want to do that stuff, then what you got to do is let me give you the and everybody. I haven't even uploaded them on the live stream the site yet, but when I do, I'm going to upload the raw images so that you can actually process them. When I say raw, I'm not going to upload the camera raw. Camera raw is a format where there's absolutely no compression, and every camera maker has a different flavor. Nikon's is NEF, Sony's is ARW, RAW is another one that's very common, RAW. But I convert them to another loss-free format, like TIFF. Okay, just an uncompressed TIFF. So the file is going to be several meg in size, but you get all the data, nothing compromised, and that's the kind of thing that's important. So that's kind of what we're going to do, up there. So you'll see it. So tonight we're going to actually look for a couple of interesting things. We're going to look for when it comes up. It rises in about 10 minutes, so we're going to have to wait quite a little bit of time here. And if I'm still doing this and the telescope is still in good shape, meaning dew-wise, I cleaned out the corrector plate and all the glass 2 days ago, and it's performing flawlessly. We're going to look at Messier 1, which is the Crab Nebula. And, you know, I've never seen the Crab Nebula through this telescope. Just like last night, I saw the Cave Nebula for the first time ever in my whole life, and I saw it through the SkyTour LiveStream scope. And then I also looked at the Orion Nebula, which of course I've seen in many different scopes except this one, and that was last night. And I was very cold. I got to the point where I was so cold that I didn't feel anything anymore. And I just said, you know what, I gotta stay now that I can do it. And so I went and did all my dark frames. And Amanda kind of babysat me to make sure I was okay, because, you know, I was just cranking away. And dark frames are boring. You know, when you take frames like, you know, like what you see on the screen here, okay?
Mm-hmm.
This is obviously the Omega Nebula, right? But I can actually show you that there's more, okay? This is the other ones. These are different frames. If you notice, they're actually changing. And you know what I'm going to do, Keith, is I'm going to share my screen with you so that you see things live. All right?
All right.
Yeah, I did that with Amanda yesterday, and I've got an internet that's 10 times faster download and twice as fast upload.
Oh, you did finally get that?
I did. So I'm in the
Nice.
process now of being able to, I'm trying to test it and stress it. So this is how we're going to do it. All right, I'm sharing a screen, and
once again on YouTube, you're looking at the
There you
beautiful M17.
Omega Nebula. Do you want to tell them what that is?
It's a nebula.
Come on, you can do better than that, can't you?
What's that?
You can do better than that.
Sure I can. It's an Omega Nebula.
There you go. Does that mean it's the last one?
Probably. No, I have no idea.
I
I'm not.
know.
Listen, I will be the first to tell you I am not versed, and I'm learning just as everybody else is.
Well-
So you're teaching me as you're teaching them.
Well, you know what though, I thought that one night you came on and you were just spewing all these wonderful factoids and stuff. It's like, wow, he's doing a great job.
Well, I do have a. But even what I was spewing that night was just minimal, basic knowledge. You know what I mean?
Well, whatever, but it's still good. You know, like, okay, well, the Omega Nebula is a star-forming region. It's actually reddish, not purplish like here. This is actually a color sensor issue, and it's also related to the fact that I'm actually using a filter. I'm using a filter on the camera right now to just get rid of any potential disastrous light in the sky. So it tends to bluify things. So the red nebula will tend to look a little more purple. But I correct those when I bring them in. And actually, I've been writing these little extra programs within Photoshop. And so what I do is, all I have to do is now hit one button that I create in Photoshop, and a whole bunch of processes get done to a photo. Really, really cool. So I have one to enhance galaxy structure. I have one to actually remove the color cast, like you see in the background.
So in a way, it's kind of automated.
Yeah.
Nice.
So if you look in the background here, it looks blue, right?
Mhm.
Well, I run that through my Photoshop filter, which I call color cast removal, and I just hit the arrow, and bam, it's gone. And I basically, they're called actions within Photoshop, and they're basically little recorded. I think of them as recording of keystrokes, but you're actually going within the functions and using the functions that Photoshop has to offer. Then I have another one which splits the color photos into red, green, and blue components. Now, in the real world of astronomy, the RGB photos, each of those images, the red image, the green image, and the blue image, are not red, green, or blue. They're black and white. Because all that's in that is information. Okay, the relative amounts of brightness tell the program, and anything you use to assemble an RGB image, tells the program how much red is in it, how much green is in it, how much blue. And I actually wrote a little simulated thing that actually takes apart a color photo and shows it in the RGB channels, they're called. The other thing is I actually simulated the Hubble palette. So I can now, with one click, I can convert the images like you see here to the palette, the color palette that the Hubble uses. And you can actually see, for instance, this broad area that you see here is H2. It's hydrogen 2, as you know, Roman numeral 2, which is singly ionized hydrogen. And this is a star-forming region, and it's the H2 is singly ionized, and so therefore, for that particular element in this nebula, it shows as a slightly greenish cast.
Now let me ask you: do you have a corrector on your telescope or camera, or is this mirrored?
No, it's I have a corrector.
Okay, so it's as you would see it with your eyes, if you could.
Yeah, I mean it's these telescopes they're called Schmidt-Cassegrain telescopes, which you know of course, but you know in talking to the folks, and the Schmidt-Cassegrain telescopes are really great for smaller observatories because they're folded optical path telescopes, meaning that the light goes down, hits the primary mirror, comes up and hits another secondary mirror that's suspended in the middle of the view through on a piece of glass, a round piece of glass that's optically clear, and then that reflection goes back down through the center of the mirror. There's a hole, and it comes out to the eyepiece. And in my case, I don't ever put eyepieces on it. I have electronics. I put either a spectral system to check out the spectra of these things, or I put my camera on it, and eventually I'll be able to put what's called a photon counter, a photometry setup on the back. And then a full-blown spectral system is going to go on here too, probably when it gets to Arizona, because I want to be able to do the spectra. And you know, a photometer is a light counter, basically. It counts how much light's coming from a star. And if a star is having a planet passing in front of it, for instance, then that's a transit if it's seen from the Earth. And those transits are the thing that the Kepler was looking for. But it's also something that amateurs can do with their freaking telescopes, believe it or not. If you generate a professional light curve and that light curve has a dip in it, you may have discovered a planet crossing in front of the star, and your data will be added to the pool of other knowledge. So there's a lot of things that you can do to contribute to the real world of astronomy. You know?
Amen.
Yeah. So let me see if I've got something in here from the other night. I don't know if I do. I might have. Let's go. Okay, I took it off.
Have you looked at the? Have you did a closer look at the Pleiades on this stream yet?
Yeah, last night we actually took a look at the Pleiades and checked out the Maya and Merope's blue nebula, reflection nebula. And I was looking to see if you must read my mind, because I was actually looking for those images to show you, but I took them off. And they're not on the camera right now because I took them off already to put them in the directory for storage. So, but that's the way it goes. What can I tell you? Yeah. So anyway, this is you're not streaming tonight?
Who, me?
Well, you know, Paul.
No. We're probably, well, you got to figure early morning after midnight.
Oh,
is the new moon.
duh. Well, I mean, you could have been looking at Saturn for a while.
So it's probably the earliest you're going to see us stream is maybe Saturday or Sunday night, and that's when we're back to waxing towards full again. And
right.
We'll start getting that short stream in, right at dusk, about a half hour to the moon sets, and then it'll just keep getting longer and longer as the days go.
Yeah. Well, that's kind of funny, right? Because when you look at what happens here, I look at a dark sky without the moon and I go, yeah. You look at the moon without the moon in the sky and you go, crap. Okay. The moon shows up for you, you go, yeah, and I go, crap. You know. Yeah. But then that's good. Complementary streams.
Have you ever looked at the what was its name? It was something crazy, something star nebula. It was a
something star nebula.
The flaming star.
Oh, yeah, the flame nebula's in Orion. Yeah. Okay. And it's right above Alnitak in Orion, the leftmost star in the belt. And I did get an image of it last night, actually, but it was really low to the horizon. I actually had the telescope was fully horizontal, looking into Orion Nebula.
I'm looking at it now, and it's a little northeast of direct east, and it's just coming up over the horizon as we speak.
Yep.
Nice.
And it's going to be a while before we actually get to see it in all its goodness. A couple more months or so. I'm moving here. Hold on. me just move into another object. Just warning you for the sound if you hear the sound. I was aligning the telescope before, trying to get its alignment right. Many times I'd start to align the telescope, it gets perfect. And then I move and like smash my head on it and it goes, eh, and it moves. It's like, oh, I gotta do it all over again. I don't know, you know, I'm a moron sometimes.
Well, I tell you, Vega's pretty much straight up right now, isn't it?
It is. And have you seen the Dumbbell Nebula? That when they
I did see it on one of your first streams. That was over here.
Really? So you haven't seen it lately?
Nah.
I mean, not that it's changed a lot, but I'm going to just do a 5 seconds here at 10,000 ISO. This is an object that some of you may know. Are you looking at the chat right now?
Yeah.
Okay. Just let me know if you see people who get this. Okay. Oops, it's off to the side. They're not going to get it if it's over there. Yeah, I knew that was going to happen. Okay, let me just bring that in. Okay, let me bring it. There we go. I see it. Okay, one more time. Okay, this is an object that's interesting because of a number of reasons. Obviously, not just because it's astronomy and I love it. There's a lot of interesting things here in this object because, yeah, I did it purposely, you know, so that it looks like that. There you go. Okay, now. Oops, this object, you may think it's a globular cluster, but it's not. Okay? Yeah,
right.
Yeah, this is actually the wild duck. Have you seen the wild
duck?
The wild duck, which is actually a cluster of stars, which is not a globular cluster. But you know what's interesting? This cluster of stars formed in a nebula. All right, and the nebula was probably right nearby. They're probably there, okay? And because the stars are not like hugely old. Well, anyway, the wild duck cluster stars, they formed in this nebula, and then their own stellar winds pushed all the gas away. All right, and the same thing with the Pleiades, because you mentioned the Pleiades before. The Pleiades formed in basically an H2 region, one of these stellar nurseries. But then when you look at the Pleiades, you don't see any of the red characteristic gas that's actually giving off light, emitting light. It's an emission nebula that you expect to see, and it's not there. And the reason is because those stars are so powerful with their stellar winds that they blew all that gas away. And now the gas is actually out there, but it's far enough away now so that the stellar winds can't ionize it and cause it to glow. So it's there, but it's just farther away from the star, just at that point where they can't ionize. You know, the interstellar medium, the space between the stars, is not empty. Okay, there's micron-sized dust all throughout the space. There's all kinds of gas all throughout space. There's molecular clouds all throughout space, mainly of diatomic hydrogen. You know, H2, you know, H numeral 2. You know, 2 hydrogen atoms, and that's really cool stuff. You know. Now, did you have anything in particular that you wanted to see? Because I'm going to take us, if you don't, to a cool little thing that I haven't seen before.
Go for it.
Okay.
If I think of anything, I'll be sure. I'll make sure it's up in the sky first of all.
Yeah, well, I could tell you that in a second too when we do it, but you're right. Okay, let's see here.
Have you taken a picture of Uranus?
But I'm bummed. Yeah, but I can't hold the phone that way. Yeah. Oh.
Have you been able to take a picture of Uranus?
You mean of Uranus?
Uranus? Uranus? Yeah.
You just turned this into a
18 and over.
18 and plus, yeah. Nah, I have actually taken a picture of Uranus and Neptune.
How's it come out with your camera?
And Pluto, by the way. I got a nice picture of Pluto too. I showed people Pluto because you can see it.
We can live stream Uranus and Neptune and whatnot, but once it comes down to Pluto, if you see it, it's still a little dot. Like we would have to be able to do a longer exposure.
Yeah,
and
but
we can't do that live unless we hook up the actual space camera.
Yeah, but one thing's interesting about Pluto, it actually has a slightly different color than the other stars.
Was it like a tinge of red? Or
yes. it has a little bit of a tinge of red. I actually have a photo of it where it actually has this little red look.
So it has like a kind of like a pinkish off-white.
No, well, you know, if you take an exposure that's not terribly terribly long, then you can actually get a nice view of it. As a dot, of course, it's always just a dot. But yeah, you can actually see it, and you can also see you can see Chiron, and I'm wondering if the other moons. I'm trying to remember.
And I do want to say welcome to everybody that is watching on YouTube and in the chat. That goes for Jenny and Ian and Nancy and Roxar and Daryl and
awesome.
Yeah, whole bunch of people in. Jello, Duplicat.
Yeah, thanks guys for coming out. I realized that I didn't announce this ahead of time. I just felt like doing it, and sometimes I do that. Okay.
Well, we are live with the SkyTour LiveStream with Mark D'Antonio. I am Keith from PNK Space Imaging, and I'm just sitting here taking in the sights with you all.
It's very nice of you to volunteer to come on in tonight. I went looking for.
I saw that you didn't have Amanda, and I was like, well, I'm not doing nothing tonight, so why not?
Well, thank you. See, you know, give Keith a shout out there in the chat. Let him know what you think of that very magnanimous.
Don't let me know what you think of me.
Magnanimous gesture. Well, you know. Let's go to. I'm going to go to this guy right now. This is another one I'm going to try.
Jenny says I have an ego. Darn right, I got an ego.
Well, everybody has one. It's a good one. You wouldn't be doing this if we didn't. You wouldn't be doing any of this stuff if you didn't have an ego.
Yeah.
You have to have an ego.
You know, is it just me, or as you get older, does your thirst for knowledge, just expand? Like, it seems like it gets more and more intense the older that you get. I wonder why that is.
You know, I can't explain it, but it has nothing to do with you're feeling your own mortality kind of thing. Because I don't have a problem with that. I mean, you know, when it's time to go, it's time to go. You know, I won't go kicking and screaming. I almost did a couple of years ago anyway. You know, so it's like, hey, I'm kind of used to that. But no, I think that it's really just unfortunate that as we get older, I think
we'll have to be honest. 10 years earlier from right now, I could have gave a crap about this, you know. But
I can see that.
As on, the more and more I learn, like I'll sit here tonight and I'll learn all this stuff from what you're showing us, and that will have my mind racing tomorrow.
Right?
Like putting pieces of the puzzle together, maybe even pieces that don't even fit together, and then you'll have me. You know, the obsessive compulsive, then hitting you up on Skype asking you questions like you did before.
Yeah, you did. It keeps funny. It keeps funny because it's like every like 4 minutes I'd get another question. But wait, what about this? And then it's like, oh, okay. You know, no speak of the English. No, I actually don't. I don't have any problem with it. It doesn't bother me at all. I'm perfectly happy to.
Yeah, well, you know, just know you don't have to answer it right away. You can always just get back to me whenever you.
Yeah.
I mean, you might have a pile of questions by the time you get back to me, but
yeah.
Still, you don't have to answer it right away by any means.
No, it's just that if I don't, then I'm gonna have a pile of questions that I have to go through. I'd much rather, you know, answer the questions.
Let me tell you, how good are the crowds on these 3 channels?
You know, they're fantastic. These people are wonderful. I would never, you know, think about it. I actually did this over 5 hours last night.
Never mind. Jenny said she spelled it wrong, and she said, Keith, you have an echo.
Oh, that's funny.
Really? I have an echo?
Yeah, you know what?
Listen on the
Bill's. It's got to do something. It has to do something with probably something to do with my
It has to be your end, dude.
It is. It's my end. I'm sure it is.
Yeah.
And you know, Bill and I went through this already once, but he's gonna drive out here to help me troubleshoot this. You know?
There you go. I'm wondering if it doesn't. I mean, obviously it wouldn't have anything to do with the music, right? Because I'm wondering why I can hear the music in my headphones.
Well, because I'm piping it through the same channel that you're coming in on.
I think that's why. I think that's your problem. You need to have its own separate channel. For
it does,
music.
But I don't have a mixer for that at this point.
Oh, yeah. Well, there's your problem.
Yeah.
You want one?
I would love one, but I don't have one.
I have 3.
You do?
Yeah.
Oh man.
I have a 2-channel, which would work great for you. Or do you need a 3 or a 4 channel?
I have a 2-channel. That's what this is. And on the second channel, Skype and the music go out. Nice. So I actually need a minimum of a 3-channel.
Yeah, let me look for it.
Okay, if you got one, that's great, and I totally appreciate it.
Yeah, and when we take that that thing down to Tennessee or Kentucky. Which one is it? Tennessee?
It's Tennessee. Yeah, don't make me go too far.
No, but I'll give it to you. I'll give it to you then.
All right, cool.
Yeah. Or if it reminds me, do you want to do that in a couple weeks?
Well, I asked my friend actually yesterday because I talked to him, and he says this month isn't going to be a good time because at the end of the month his daughter's getting married, and he's just pulling his hair out. So unfortunately, we can't do it in a couple weeks. So it's going to be a little longer.
What about November?
Well, he's coming up here in November, but at least he's supposed to. But they don't even know if they can do that. But we'll see. I mean, I'm game for any time. It's just that I gotta
do you have to help them build it, or is it just
no.
take down and drop off?
Yes, it's a take down, drop off. Folks, we're talking about the extra observatory dome that's at the bottom of my property here. So when you're driving down the road, you see this big white dome just sitting in the ground. It looks like it's some kind of facility, like a a NORAD site or something. You know.
I'd agree with that.
Yeah, it's just amazing.
Yeah.
Okay.
That's cool.
Yeah, it's very cool.
Well, we can do it. We can definitely figure it out.
Yeah,
I was just saying, because the end of this month would work really good for me to do it.
Yeah, because you probably don't have a whole lot going on, right, with work?
Exactly. Yep. And then we're going to start picking up for Christmas,
Oh, yeah.
come November. But,
That's going to be just exciting.
Mm-hmm.
Yes, it will.
All right, what are we going to look at now?
I'm going to this object. I'm about to go to this object right now. I don't like to actually say the object ahead of time because, I don't want to give it away. But this is one that I actually spent some time studying. Let's see, NGC. The NGC number on it, for those who want to know, is 7635.
NGC 7635.
Right. Look at Keith typing it in, finding out what it is.
Yeah, I'm actually typing it into Stellarium.
Oh, okay.
So I like to see it compared to and compare what they have here to what you put up on the screen.
Yes.
Which is very similar, by the way. You want to zoom in on it.
Cool. There we go. It's very high in the sky, so we shouldn't have any problem viewing this.
You said NGC, what's the number again?
7635.
7635.
7635.
And there we have it. Ooh.
Let's see what we got.
The bubble.
Yeah, the bumble. Mr. Bumble. I'm actually going to do a little 4K acquisition, see if I got it.
What is a filamentary structure?
The filamentary structure is the structure that you'll see.
Is that the actual bubble?
Yes. I mean, that's typically what it is. Now, I'm trying to see if I've actually got it in the view, and I can't tell with the 4K. It's rather faint. So I'm gonna do let's see. Let's go down to 20,000 for 15 seconds. ASA 20,000 for 15 seconds, and see what we get. So this will be a acquisition.
Sorry, Dale, I didn't mean to give it away.
Oh, well, it wasn't a contest today,
Yeah.
I'm actually wearing gloves. I'm wearing a hat. Okay, I've got.
You're out there looking like a kid from South Park.
I actually do. I have that very hat. I have that very type of hat, in fact. Someone say, "Hey, Stan! You're an idiot, Stan. Screw you guys. I'm going home." All right, there it is. I think.
Yes, I'm going to Jupiter.
Ha ha. Ha 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 ha. Okay, it's right down the bottom. So I'm gonna.
Oh yeah.
Yeah. Hold on. I'm gonna just bring it up. I thought it was there. I just had to bring it up now with the view here. I'm moving the telescope with my iPad. I have a Wi-Fi connection, which Keith knows all about because he's familiar with the iPad and the types of connections we can do. Now I'm going to do, because I know where it is now, I'm going to do 25 seconds. Actually, I'll do 25 seconds at 20,000. Now here's an interesting thing. When people think about making a time exposure, they say, "Oh, I can take a 10-second exposure at this particular speed," and then they say, "Wait, if I just do one that's like 10 times as long, I'll get 10 times as much data." And the answer, of course, is actually you don't. In fact, at a certain point, you just start building up a sky background, and it ends up blowing out the image, and you don't get any more data. And I did a test to show that earlier with the Omega Nebula that we had up, and I didn't publicize it here because I wasn't ready to show it. But the thing was, I did a shot 15 seconds at 10,000 ASA, ISO, and then I did a shot 20 seconds at 10,000 ISO. Yeah, look at that. And that shot,
dead center.
Yeah, that shot at 10,000 ISO looked identical to the shot for 20 seconds because all of the delicate detail had already come in. There was nothing more you could get by adding 10 more seconds. Yeah, here we go. This is the bubble. Now, what's interesting about the bubble is that this star in the center is so energetic. It's pumping out so much radiation that it's actually pushing the gas away from the star at a very high rate. And let me zoom in. What's happening is it's actually colliding with the interstellar medium. You see how that bubble has like an arch over it? Well, that glow is because of the fact that the atoms in this gas, mostly hydrogen, are actually now emitting light because they are forced to be ionized. They lose an electron. Well, an electron goes to a higher state, and then it spontaneously drops down. When it does that, it emits light, characteristic red, like you see here in the image. And this bubble is actually much larger. Now, I don't think we can see it in this shot, but the bubble actually, you can see kind of a little semblance of a dead center there. There's a little piece of the other end of the bubble here. It's sort of an oblong looking shape, all right? And I could do a longer exposure, and I will, just to show you after. But the reason is that this is so off-center, and this star that you see right there, that is the thing. That star in there is the thing that's causing this. All right? So you say, well, why is it so close here, but so far away, so close at the top, but so far away down at the bottom? There's no perspective thing you can do in 3D to make that work. So the reason that it's doing what we see is because if you look to the left of the bubble itself, you see more stuff. As the star is blowing gas off to that upper left area, it's actually encountering a very dense interstellar medium. There's more atoms per cubic centimeter there of more gas than behind it and down below. So what happens is the cloud expands almost freely down below, but it's restricted to an expansion to the northeast, up and to the left. Okay, so this is what happens, all right, and this is what we see with nebulae. Sometimes the central star that's firing and powering up these nebulae are actually not even centered, and the reason is because the interstellar medium's not even all the way around. And you get this all the time. Let me just do one quick shot here. I'm going to go and jump up to 51,200 for 25 seconds. All right. Because I want to see if I can catch that lower piece of the shell down below. This is called a shell. This thing that's popped off here. Well, it made a shell. It's not from like a planetary nebula where a star is dying. This is actually a very hot young star. It's just that when the star winked on and began nuclear fusion, it began to push the gas and dust away. And as it did so, that leading edge is called a shock front. As it did so, it began to ionize that gas. And there's stars in other objects that I'll show you.
Is that the only star in there?
Well, yes, it's the only star in that nebular region where this is actually illuminated. Okay. And this is a star which is actually doing it. Okay, now we come back to this. All right, now if you look down below the bubble itself, you'll see there's some more red down below. Okay, and let me just zoom in to kind of make that clearer. Now we have noise in the image, of course, because we're doing this very noisily with a very high ISO. But that extent right there on the screen, right about there, say right there. From there, no, not quite, a little more up here and then come up. There we go. So where the bubble is at the very top, and down at the bottom, where you see the little down arrow where the word zoom out is, okay, there's a little piece of red down there, and that's actually the other end of this bubble. Yeah, it's actually pretty cool. And but because the interstellar medium is so dense up by the star, it's not making much headway into the interstellar medium there. But it's oddly very symmetrical. It's got a beautiful, hemispherical view to it, because that shock front is close to the star, and so the star is actually very powerfully pushing stellar winds out, and it's actually able to make that a relatively circular pattern. It's really nice. But that's the that's this guy, okay, and this is the Bubble Nebula. Ain't it cool?
Gorgeous.
It is actually pretty, and the thing is, you can't see it with your eye. All these things in the interstellar medium, all these things in the sky that people just don't know are there. You know.
And we did have Jenny mentioning the Seven Sisters.
Yeah, the Pleiades. Yep. When I looked at them last night, right now they're still a little bit in the murk, and I call murk the air mass, the distance. It's sort of on an angle, probably about 20 degrees right now, and they have to raise up a little higher before we can start playing around and getting some nebulosity views. Let me try this guy. This is another one I'm going to try. I imaged it yesterday, and I also put it up online, and it was just quite beautiful. Okay.
And anybody that has good viewing sky in a nice dark area, you will catch the Milky Way in the southwest sky.
Yes, you will.
If you want to see it.
Okay, here we go. All right. Let's see here. This is an object that's actually right in Cygnus. Okay. And I gotta wait. There we go. We're stuck in there. And now what I'm gonna do is I'll do an acquisition image here. Let me just try it with. Let me try it with the 4K thing. Let's see if I can see it. It's not that bright. Oh, this is the Purina Puppy Chow commercial music. Just be kind to your little buddy, because your little buddy's going to be around for a long time.
Yeah,
Purina.
right. By the way, Mark, I just want to let you know that I am looking at Uranus.
18 plus. Okay.
The planet, you pervert.
Ooh. You're so funny.
It's 100% illuminated. It's kind of hard to miss out there.
Yeah, it's true. What are you looking at it with?
Stellarium.
Oh, okay. Very cool.
Checking out the orbits, which are many.
Yeah. Well, it's got a number of moons. And Uranus is also, one of these planets that's actually leaning over on its side, which is kind of interesting. How that happened in our solar system, we actually don't really quite have a good understanding of. We know why our Earth is on a tilted axis. We know why the moon is oblate. We understand that, but it's really dead center. Look at that! Holy cow!
Wow!
I wasn't even sure, but there it is. Yeah, that's the this is the Crescent Nebula, and actually I'm gonna move us up a little bit because it's got to go up a little more.
Got to go up just a tad.
Yeah, it's going up just a little bit of a tailor. There we go. Oh, so much fun.
Here it is. Okay, so this is the this should be good because I want to show the lower half of it as well. Because this object here is really interesting. It's both an emission nebula and a planetary nebula. Yeah. See, what happens is, you know, at some point over time, planetary nebula become emission nebula, or can be classified as emission nebula, if there's another star that can heat them up, heat up the gas and ionize the gas. And that's exactly what happens here. Now, if you noticed in this shot here, okay, this is the Crescent Nebula, and there is a star that you can't really discern amongst all the other stars, I'm sure. But let me just, first of all, let me see if I can get rid of some of this stuff here. Okay, that's the wrong thing to get rid of. Here we go. Okay, so now, see down by at the bottom here, there's another, right above the word zoom in, you can see the lower half. This actually has another name, this nebula. It's actually the Crescent Nebula, but it's actually, it's also known as the Euro Nebula. And that's because it's a backwards Euro symbol. Okay, you see where that bright star is in the middle? Yeah.
V1770CYG.
Very good. Exactly. So now what we're looking at, okay, is this is the backwards Euro symbol, and you'll notice that at the top, okay, this star, this object.
It sounds like you're giving a lesson from an old-timey bar.
Doesn't it though?
Because of the music.
Yeah.
It's like, hey, Pete, play us out.
I'm using here.
Yeah.
Oh, that's
Sorry,
right.
go ahead.
No, it's cool.
Now you're hearing the music.
Now I can. Yeah. Now. Well, I knew the music was there, but you know, I picked it. Hey, I played the Can before. Didn't you hear it?
Yeah.
Well, it's a good thing I didn't start singing the Elements song. You know.
Oh boy.
That's it. This is the periodic table. Normal gas is stable. Yes. Halogens and alkali react aggressively. Each period will see new outer shells with the electrons that are added moving to the right. Yeah. Okay.
I'll tell you what. If you want to lay down that track, if you ever get down this way, I'll put you in the studio and we'll mic it up and we'll lay that track down, and then I'll mix it and put a beat on it, and then we'll make a video, a science video.
Oh, that would be hilarious. It's been done before, but you know.
Ain't never been done my way.
Yeah, that's true. That's true. You know, I'm looking out right now, and I've actually got a. I'm looking at a very strange object up in the sky. It's blinking like an aircraft, but it's not moving.
Well, get to it.
Huh. I'm sure it's moving. It's just it's foreshortened, and I don't see it because it's probably high.
Get to it.
Wow, that's pretty interesting. I mean, anyway, so going back to the Crescent Nebula. Oh, look, it's emitting a blue beam. Oh, there's Travis. So when we see the crescent here, one thing that we have to understand is that star you see right there in the middle, that one right there. Okay, right there. It's as close to the center as possible. The bright one. That's actually a special star. It's called a Wolf-Rayet star, and the Wolf-Rayet stars are very powerful. They're well known for a number of things, including having emission lines where most stars have absorption lines. For instance, when we look at the sun's outer atmosphere is a lot cooler than the atmosphere in the core of the star, or, you know, the rarefied plasma in the core of the star. So when the energy goes coursing through that outer atmosphere of the star, like our sun, the atoms in the outer atmosphere are absorbing some of the energy coming through them, and they form like a dark line in the star spectrum. And because of, you know, the material that the atoms are made of, the elements, okay, whatever they are, if they're calcium or if they're magnesium, those lines are absorbed always at the same place in the spectrum. So we can identify what a star is made of simply by looking at the spectrum and figuring out which lines belong to which. Now the weird thing is the Wolf-Rayet stars, like this guy, these stars have emission lines. Now, what's that mean? Emission lines are not absorption lines, obviously. An emission line is a line, for instance, where in the spectrum where it's a bright line. It's giving off light. It's not absorbing energy. It's giving off energy. So wait a minute, how can that happen? That would almost imply that the outer atmosphere of the star is hotter than the inner part of the star. And in a sense, that's kind of right, except the star itself is usually a giant star. All right, but what happens is these Wolf-Rayet stars will have a shroud of gas around them. And the gas is usually associated with a star like this one. Okay, this is a star that has died, and what has happened is it actually has pumped a lot of energy out into the interstellar medium. And Wolf-Rayet stars have temperatures.
Do me a favor, just for anybody that doesn't know. You want to define interstellar medium?
Yes, it's a psychic who lives in another star system. No, interstellar medium is the space between the stars.
There you go.
So, and when you look at this guy here, this star we're just talking about in the center, pretty much, it has such a copious high energy radiation that it's pumping out, that what happens is the radiation goes out. All right, it's a very hot star, and then the radiation hits this gas that you see, the red at the top and a little bit down at the bottom. Well, that gas that you see there came at a different time in the star's evolution. That happened when the star was a red giant, and it sloughed off its outer layers. That particular gas is moving slowly through the interstellar medium, and when the radiation from this star hits it, okay, now it actually ionizes it and causes it to glow. That's what we're seeing here. But what happens is another amazing thing. That radiation hits that cloud of gas and dust, mostly gas actually, around the star, and then it gets reflected back, in a sense. And when it comes back in, it collides with more stuff that's outgoing. And the net result is that it heats up the area around the star to over 200,000 degrees Kelvin, which is extremely hot. It's the hottest thing in the universe, besides the core of a star. Okay, it's the hottest, feature, the non-star feature in the universe. And so, when these Wolf-Rayet stars do this, that's why they show these emission lines, because now that hot gas is emitting at a spectral frequency that is very characteristic of that particular gas, which is many times it can be oxygen, it can be hydrogen, it can also be carbon. So it's really interesting to see how these Wolf-Rayet stars actually generate what they do. So I wanted to show you the Crescent Nebula for this reason. I wanted you to see that this thing is just it's up there in Cygnus. You could miss it very easily, but you can actually see it almost looks three-dimensional, because you can actually see how the glow on this is actually changing aspect ratios. It's going kind of around through the gas. You can almost see how the Hubble telescope will actually create a really phenomenal image of this, and Hubble has actually created a phenomenal image of the crescent. So I can't see the chat right now, so I don't know if anyone's got any questions.
I don't see any yet. A lot of people just hanging out.
Okay, no problem. That's good. That's fine. That's fine. That's fine.
Yep. Jenny says amazing. Amazing, Mark.
Well, I'm glad they're having a good time with that.
Let's see. Yeah, I don't see any questions in the chat.
All right.
So,
I mean, not that I expect you to go running through the chat. You just came on board to help out, and I love it. I appreciate it. And I haven't talked to you in a long time.
I have it up on screen, so I'll see it.
Okay. Yeah, I haven't talked to you for a while.
I know, right? It seems like a while.
Yeah, I know. It's just crazy. Okay, let's go here. I want to do this guy. I want to take us to a different place. And the reason I want to do this is because, and I'm going to go here now. I just want to show this object to you. It's right near this, but it kind of makes sense to show it after showing you this Wolf-Rayet star.
All right.
So that's where we're going now. There it is. Can't miss it. It'll be pretty much dead center here. It's a little off, but it's all right. Okay, now we're looking right now at a star that is very orange. and I'm going to do an acquisition shot. I call it 6 seconds at 25,600, just to kind of get the background stars in there as well. We are in Cygnus, so it's going to be a fairly extensive star field. And you'll see it kind of looks hazy when we're done. Okay, look at that. This is beautiful. Now, if we just go into this image, it rotates. I hate that. I got to figure out how to stop that from happening. But
oh, you went vertical.
I hate that. That's what I'm saying. But check that out. That orange star sitting right out in the middle of nowhere, that's an amazing star because it's called a carbon star. Now, these stars have built up an excess of carbon in their cores, and they're giant stars. Okay.
Wait, what star is this?
This is TT Cygni, as in Tango Cygni, Cygnus.
Okay.
Yeah, TT Cygni. Look it up. Oh, I just saw a meteor. Wow. That was cool. It kind of went down from Cygnus westward. So, yeah, TT Cygni is a carbon star, and the carbon stars are all kind of in the same family. They're all pretty much identical in what they, how they look and what they do. It's also a double star, and I don't think we can actually. I don't think we can see the component, although.
Now on Stellarium, it has this thing that says period, 118 days.
Well, that's because it's a variable star as well. Most of the carbon stars are. That means that over a period of time, they will vary their brightness. And yeah, and TT Cygni is it's called a pulsating semi-regular variable. Okay.
An SRB.
An SRB, that's correct. Its magnitude varies from like 10.2 to 11.9. So remember, in the magnitude scale in astronomy, the larger the number, the fainter the star. So like Vega is 0.05, okay, in brightness, so it's very bright. Negative stars, Sun is minus 26, for instance. Okay, so you can see that this scale is kind of odd. Astronomers, we do it all different. Astronomy, we do it differently, that kind of thing. So this is a pulsating semi-regular variable, like I said, and it has a 118-day period, like you said. That means that it varies in that cycle. It's fairly regular. Some are irregular, where they can change on the fly, and suddenly they're doing totally different things. But most of the carbon stars like this are actually a little bit more regular. You know,
Yeah.
So it's pretty cool. You know, these guys are really neat. I gotta tell you. You know,
Color index B-V.
B minus V.
Yep.
Yeah, blue minus visual. So
it is kind of just sitting there, isn't it?
yeah, it's
Kind of in the middle.
It's a beautiful star. Yeah. Now, let's go take a look at another one, and it's also right nearby. But let's take a look at this carbon star as well. I've gone through carbon stars before, but it's time to visit them again. And you can tell the telescope didn't even move very far. You know, and so again, and now look at that, right there in the center of the screen. Okay, that's a cool star. Okay, and it is a cool star, temperature-wise as well. Okay, this is an 8th magnitude variable star that we're seeing here. And let me just do a live in a live view here. Let me just kind of come into this. I just want you to see the colors. Okay, I'm going to move it over a little bit.
I just saw blinking by that area.
Check it out.
Was that a plane?
No, that was probably a. Let me see. Let me look and make sure. Yeah, no, it wasn't a plane. That was actually a pixel on the camera, because you can see blinking red now. Okay, but check that out. You're seeing this carbon star, all right, and carbon stars are rated on a different scale from other stars. You know how we have the OB, AF, GK, M scale for stellar classification. Well, carbon stars are rated on what's called the C scale. Okay, this one is actually very close to the farthest end, lowest temperature carbon star, and it literally it's putting out brightness. It's that orange thing, obviously, in the screen, almost red. It's putting out 92 times the luminosity or brightness of the sun, and that's because it's a giant star.
Well, let me ask you, what do they mean by photometric system?
Well, see, there's different magnitude systems, that is, measures of brightness for stars, and there are a number of different ways that we can measure the brightness of a star. We have B minus V. Okay, we have UBV. We have other ways, and so
that last one we were on, that TTSig is it said photometric system B. So
yeah,
I was just wondering what that.
Yeah, that doesn't mean that's actually not for like it's a B-type star. Okay, there is no classification in the regular stellar classification for these guys. Let's take a picture though, so I can show you what this looks like, and we'll do. Let's see. We'll do 6 seconds at 25,600 again, just to kind of get a view of the field. We're kind of in the northern Cygnus Milky Way region. Okay, just around the just north of the North American Nebula, in fact.
Jenny, Jenny's wondering why I have echo. It's on Mark's end.
It's me. It's all my fault.
Has an echo for some reason. I'm not sure. We haven't figured it out yet.
Yeah. Look at this. This is gorgeous. This is absolutely gorgeous. Okay. You can see the carbon star there, and again, it's a double star. Hang on. I might wait. Hold on. It's not a double star. Sorry. My apologies. It's actually, that's just a field star that looks like it's right nearby. Okay, this is actually called it's a Mira type variable, M-I-R-A, a Mira variable, and it's a pulsating variable. It goes from magnitude 5.9, okay, to 12.1 in like a 460-day interval. So, if we looked at this star in a month, we would actually see a different brightness for the star relative to that blue star we see in the field. And then another month later, a different brightness still. 5.9 is just, here's what's interesting, 5.9 is just at the end of the limit for what you could see with your eye. You can't really see 5.9, but it's the difference between seeing a 5.9 star with binoculars and not being able to see the star at all. Okay, that's how much it varies. That's what's incredible about this particular star. Yeah, it's amazing. So this is a carbon star like that, and when we talked about the Wolf-Rayet stars, we talked about them as being very big giants as well, and they're actually what are called AGB stars, and that stands for asymptotic giant branch stars in the stellar evolution world. And most stars go through this phase. When the sun starts to become a red giant, it's going to go through the AGB path as well. But the stars that are Wolf-Rayet stars actually have a lot of energy to burn, basically. So there's a tremendous amount of stuff we can learn from them still, even with them doing what they are. So let's see. Let me go and I think the carbon stars are really pretty. That's why I'm showing you these tonight.
Yeah, they're definitely different.
Because they're so startlingly red. Barnard star is very red. It's a red dwarf though. It's not a giant like these. Well, you know what? Some stars can be carbon stars that are just regular normal dwarfs, like the sun is a normal dwarf. But that's very, very rare. Usually they're just big AGB, off the main sequence, that is the normal hydrogen fusing sequence of stars. They're off in another world doing different things, making carbon, okay, which means they have to be massive enough to fuse carbon and oxygen. But they basically don't have a lot of small stars in them, Now let's see, if I go to this one, I can pretty much stay right where I am. I may not even have to move the dome. Okay, this is another. Let's go see. Let's go see, Captain. Oh, look at that. See how red that is? That's just absolutely incredible. It's the only star you can see. Now this star is called T Lyrae. It's in Lyra. It's T Lyrae. It's an 8th magnitude variable star. It's in Lyra, and it's 2,346 light years from our solar system. All right, and it's a really red star. It's measured on that C scale I told you about before as a C 6.5. Remember the other one was a C 9.2, so this one's actually less red. But its energy output is 230 times that of our sun. Okay, so that's really incredible. Now, this one will vary from a less of a range than the other. It goes from a magnitude of 7.8 to about 9.6 or so. But it's doesn't have any kind of a regular period to it. It's sort of an irregular, and that's what it's called. It's called an irregular variable. So this is actually aiming right almost at the top of the house. So I'm not sure what the quality is going to be because we do have some heat rising off the house from the heating today, but we'll see what it looks like. Might be good.
Let's check it out.
Let's check it out. So, yeah, check it out. Yeah, check it out. Check it. Yeah, okay, check it out.
Oh yeah, look at that. I mean, in that field, I mean, it almost looks like it's not. Oh, here we go again. It almost looks like it's not real, you know? It almost looks like that isn't real. It could almost be an image artifact. Oh wait, it is. No, I'm just kidding. Actually, that looks so beautiful. I mean, that's that star. Can you imagine if you're in a planet around that star? You know, it's so red, you wouldn't see color the same way. You know, I have Wi-Fi lights in my office, so I can yell at Siri. Well, you saw them, Keith. You know, I can say, "Hey Siri, turn the lights red," and then the lights turn red. And you see that every color around you, if it's complementary to red, you'll see it. If it's not, then it's almost kind of mushy and invisible. So people living on a planet around a star like this probably would develop very different optical capabilities. Their eyes would not evolve like ours. They would not be sensitive to the green. They might be more sensitive in the red part of the spectrum. All right, and that's something that's interesting too, because you know, when we talk about other worlds and other races and other possible life, we have to understand that we might actually find very much so that we would have a very different set of life forms.
That's actually been said by a lot of abductees, saying the large almond-shaped eyes, that dark on their eyes is actually a lens.
I've heard that, actually. I have heard that. I do think that's pretty cool. Now, where am I going? I want to go to this guy. I'm taking us here right now, as you'll see, because, well, it's nearby, for one thing, but I also, I want to point out something and show you something that you actually might have mentioned this.
Uranus?
No, I could go there.
Okay.
I'm still looking at Uranus.
Stellarium. Yeah, you're I don't know what's going on there.
It's fascinating, just the tilt of it, and looking at the orbit patterns of you know, Miranda and Ariel, and you know, just kind of weird.
Yeah, and why it did that, why it's on that angle, we actually don't really know.
Such a beautiful planet for such an unfortunate name.
Yeah, I know, huh? Such a beautiful planet with such an unfortunate name. That's funny.
It is. It's a gorgeous planet.
Hey, it's not Uranus's fault. He got named that stuff.
I wonder where that name comes from, Uranus.
Oh, well, that one we can figure out. Now, you're in Stellarium, right?
Yeah.
Oh, why don't you look it up? I'll bet you can find that out.
I probably could.
All right. Now, let me just do a quick acquisition shot here. Actually, where are we? Is it in here? Yeah, there it is. Ta-da. Okay. All right, hang on 1 second.
So its original name was Uranus,
Oh,
which
interesting.
I think sounds a lot better.
Yeah, that would be a great name.
Uranus sounds so much better, and then it's the name of the husband of Gaia,
Oh,
and then the
okay.
father of the Titans in the Greek mythology. His name is derived from Uranus, meaning the heavens. This is also the name of the seventh planet in the solar system.
Wow.
Why don't they change it to Uranus? That would be so much better.
It would. It would be. That'd be a very cool name.
So you got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus. Uranus.
But that's why, because you're not quite sure how to pronounce it.
I think it's just spelled. Well, it's actually spelled like Uranus.
That's funny.
It is. It's Uranus. But it's not going to be mistaken. Like this is actually anus. This is anus.
Actually, I think that it was actually pronounced Uranus. I think that OU was Ur, but I could be wrong. So check this out now, Keith. This is the dumbbell, okay? And check out the absolute
dumbbell.
I am, I know. Check that out. Is that not like the cat's butt? I said that so I didn't have to say the cat's ass. Oh,
That is the bee's knees.
that's right. And yeah, check that out. So what's interesting is, we talked about this.
Looks like a raindrop.
Kinda. Really?
I think so.
Oh, I see that.
The whole thing, not just the interior.
Oh, okay. Yeah, this the Dumbbell Nebula is a very fascinating object. It has been for a long time for me because it's actually not the closest planetary nebula to us. We talked about that yesterday. It's the Helix. All right, but this particular guy is literally 1,400 light years away. And it's really kind of hard to tell the distance of these things because of the moving gas that's coming out from these. This is obviously the remnant of a dead star, a dying star. That central white dot you see in the middle, that's a white dwarf. And most of the white dwarfs actually have a composition such that they're mostly carbon and oxygen on their surfaces. And that their surfaces are actually more of a surface than a regular star would have, because a regular star doesn't have a surface per se. It's a transition zone, right? It goes from the outer, from the corona to the photosphere of a star like our sun. But that's not like a hard surface. You can actually, when you got near to it, it would be like going into clouds, right? You would have just very hot clouds. It would be kind of a gradual transition to denser and denser material. That's how the edge of the star would be. But when we look at the white dwarfs, it's not really like that. White dwarfs actually have a solid appearing surface in a way, because this is what's called degenerate material. And this degenerate material has a certain level of resistance to further compression. All right, and that's due to something called electron degeneracy pressure. But don't worry about the term. Just understand that white dwarfs have to be within a certain size to be white dwarfs. If they're a little bit more massive, then they could collapse further and become, say, a neutron star. And if more massive still, then they could be collapsing and cause be caused to form into a black hole. So
the bottom left of that nebula, kind of center, not the left of the actual bubble there, but where it gets brightened up. That's pretty dense stuff, huh?
Right here you're talking about?
For a nebula?
Right there?
Yeah.
Yeah, that's actually interesting because we don't know what the morphology is of that. We don't know what we're actually looking at. Are we looking at several overlaying? Not sure. You know what I mean?
Right, and I'm looking at it on Stellarium. It does have a picture, and of course, it does more colors and whatnot.
Right.
And I'm looking at it, and it's looking like, well, I don't know, because it has like a lot of red bleeding into that area of a different dust, I guess.
It does.
So,
well, it's gas. Yeah, not dust. It's gas.
Yeah, gas.
But it's sorry. I mean,
so it's a really dense, from our viewpoint, real dense area of the red and the blue gas. So, yeah.
Absolutely. And when you say dense, what does that mean?
Well, dense to our perspective.
In nebular terms, dense could mean 10,000 atoms per cubic centimeter.
Yeah.
Okay, that's dense, and that's immensely. That's almost vacuum for us. You know, if our atmosphere was that dense, we couldn't survive, obviously, more than a split second, and we would just explode outward because the pressure of 14.7 pounds per square inch that is pressing out from inside our bodies would just keep right on going without the countermanding pressure of the atmosphere pressing down at 14.7 pounds per square inch. That's why when you climb a mountain, for instance, your ears pop, because your inner pressure doesn't change. It just equalizes with the outside as best it can, but it doesn't change. When astronauts go into space, if the capsules are kept at a lower pressure, which sometimes they are, then what happens is the crew people end up getting swelling all over their body because their bodies are expanding outward from inside.
Right.
And so it could be pretty disastrous if it would go right to 0, of course. But you know, when you're in 0G, also you don't have a heart fighting gravity. It's more even, so your limbs would tend to grow, and you do get swelling around your body, just normally. Even at
Let me say to
one
anybody
atmosphere.
in the chat that the stream was buffering for, you can just F5 it, or you can refresh, and it should take care of it.
It's
So,
buffering.
you know, yeah, it started buffering for like almost everybody at the same time.
That's interesting, because that happened last night. We actually lost the stream twice.
Really?
Yeah, and then it came back, and then it never on the replay it never showed up, because you know YouTube has this way of fixing it.
Yeah.
You know.
Yeah. But for anybody in the chat there, anybody watching that's not in the chat, you can just refresh it, and you should be good.
Cool. Yeah, because I'm not looking at the chat. I never get to. You know, because I'm doing 5 things at once in the observatory, which is why sometimes I sound a little disjointed when I talk. You know, but
No, never.
no, I mean it's really potatoes. I mean, really, it's just, you know. Yeah.
Oh, kitty.
Yeah, right here. Oh, look at the squirrel. Yeah. So this is the dumbbell. It's a planetary nebula, and what's interesting about planetaries, of course, is they are just amazing. They actually populate the interstellar medium along with supernovae and emerging neutron stars with the elements for our periodic table. And we're looking at right here, the blue is sort of this ionized oxygen. But once the oxygen is no longer ionized, it's going to go back to just the ground state. That is the uncharged, no net positive charge on the atom anymore. And that'll be swept up into the formation of another planet someday, perhaps. And then the white dwarf is just doomed to just cool down. Now, because white dwarfs, we're seeing this thing from 1,400 light years away, right? That white dwarf. It's very powerful in the ultraviolet, and that's what's causing this gas to ionize. The outer rim is red. That's hydrogen gas out there that's ionizing, okay? And the ionizing oxygen is actually doubly ionized oxygen, and that's O3 actually, and that shows up very, very prominently, of course. Now, the white dwarf doesn't have any nuclear fusion going on of its own. They call them white dwarf stars. Well, actually, they're just really not stars so much. Yes, they came from stars. The progenitor was a star. You're just looking at the ultra-hot core left over. And most of the stuff in that core was already degenerate material that couldn't do fusion anymore. And that's basically why the star ended up dying, because there was no more fuel. And the way it works is when a star runs out of hydrogen, like our sun runs out of hydrogen, what happens is now the outward radiation pressure of the star is lessened because the hydrogen in the core that was being fused into helium has stopped functioning or has lessened as it starts to run out. So the star that had this, what's called a hydrostatic equilibrium, the pressure pushing out was as much as the gravity pulling in. And so the star maintains its shape that way. But if you upset the amount of energy going out, then the star is going to contract. And when it contracts and shrinks, well, there's a couple things that happen. Number one, it gets hot, all right? And number two, it begins to, the star begins to get smaller in diameter. So when that happens, and the center temperature rises enough, it reaches that magic point where the helium that's just hanging around in that core can start to fuse itself into carbon and other elements beyond. And when that happens, that's called the helium flash. I mentioned that yesterday, actually. And the helium flash is what starts lighting up the star again. It has renewed life for a period of time, and the star then begins to swell again, goes back to a larger size. But in fact, because the helium is so predominant in the center of the star, it just keeps on going, and it bloats into a red giant. And what this means is the outer layers of that star cool as they get farther away from the star. Right, so the outer temperature of the red giant is going to go down to like 3,800 degrees Kelvin or 4,000 degrees. Okay, perhaps when it might have been, 10 to 15,000 earlier. And when that happens, when those layers cool, they also get redder. They change their color, and that's why it turns into a red giant and not like a purple giant or something. So. Now the red giant stars are massive, of course, because the star is now in a state of final. It's a final phase actually for the star, where it no longer has the ability to burn a copious fuel source and fuse a copious fuel source. So now when the helium runs out, then the star contracts again, and if the star is massive enough, it might be able to start fusing carbon into nitrogen and oxygen, and then that process continues a little bit, and then what happens is you end up finding yourself in a place where the star can no longer fuse anything in its core because the fusible elements have already been made, and it usually stops at number 26, which is iron in the periodic table. And when that happens, now the star is at a crossroads. A couple things can happen. If the star has iron in its core, it means it was a massive star. So when that final fusion layer shuts down, and I say layer because it's sort of like onion skin, okay, like an onion skin layers of fusion going on in shells within the star. When that final fusion stops, then the star catastrophically collapses, okay, and that's for bigger stars than this one was here that we're seeing. And when that happens, that mass of the star from all sides comes down and crashes onto that core. And that causes a supernova. It causes a massive explosion, the biggest explosion, second biggest explosion that we know of in the universe. The third biggest explosion. The first biggest was the Big Bang. The second biggest is the kilonova that we learned about a couple days ago, when we saw that two colliding neutron stars from a galaxy 130 million light years away generated gravity waves.
Think about that. Two colliding neutron stars.
Yes, and that means stars made entirely of neutrons. But let me just finish the point, and I'll come back to that, because that's actually going down the path I'm going to go. So when that star does obliterate itself, what can be left behind is a pulsar. That is a stellar core that's spinning very rapidly. Because here's another one to really hurt your brain. When a star explodes, it doesn't explode kind of evenly in all directions. It'll explode in one direction a little bit more maybe than the other. Maybe it has to do with the fact that these large stars, as it turns out, don't have very normal outer atmospheres. They actually have these giant bubbles which come off of them. Betelgeuse is an example. It has these massive bubbles on the side. It looks like blisters of material that are coming off. And because the star is so massive, there's not a whole lot of gravitational force trying to pull those big blisters back in. And they're actually being pushed out with this radiative energy, and they just sit out there for a while. So the star kind of undulates on the outside. And so if the fusion stops suddenly, a star which has this kind of architecture collapses, but it collapses kind of unevenly. The big blister will hit the core later, after, say, another area that doesn't have a blister on it. And that causes this uneven motion to be imparted to the remaining core. And we see pulsars, for instance, which we call them pulsars because they pulse. They're spinning very rapidly.
Are there any pulsars in our viewing area?
Yeah, well, I'm kind of waiting to see if the Crab Nebula comes up, because at the center of the Crab Nebula is a pulsar. And if you look up the rate at which the pulsar in the Crab Nebula spins, okay, you'll be astounded. But then you'll be even more astounded when you hear that the fastest pulsar that we've ever seen is a star that's several miles across now, with a teaspoonful of material would weigh, a couple billion tons, literally. The star, several miles across, can spin at this unbelievable rate, and has been clocked at spinning at over 740 times per second.
Jeez.
Yeah. Okay.
That's a strobe light.
It's a strobe light that's almost looks like a continuous light.
Yeah.
740 times per second. Think about it. When you look at your fluorescent lights, they're flashing at 60 times per second. Okay, and you don't see anything different. If you blink the wrong way, sometimes you can actually see a little flicker in your fluorescent light tubes. All right. However, 740 times per second is a very high flash rate, and there's that pulsar is doing that. So it basically looks like just one continuous band of light.
That had to take some really sensitive lighting equipment to find that pulsar initially. If it's spinning that fast.
It is, and I think that again, what they do is by using an interferometer, you can actually gauge that. The process, the concept of an interferometer is actually pretty easy. You have a telescope, say, at one end of your array, and a few miles away you've got another telescope connected to the same central hub. You're looking at the same object, and you just detect when you get a pulse of light. And you detect that pulse of light at a certain very precise time, like an atomic time clock to many significant figures of accuracy. And then you compare that to the rate of time, the time clock when the other pulse arrived at the other detector, the other part of that array. And you'll see that there's a slight difference. And from that...
I know, but I mean, that had to be some really technical stuff to even detect. I mean, 700 sometimes a second.
Yeah. Look it up. You're in front of the computer. Yeah, look it up. Say fastest known pulsar, and you'll find it's 714 or 740, something like that, times per second. And they don't slow down. They're going to spin like that because there's nothing to stop them. Nothing to stop them. Now, the dumbbell nebula, like we're looking at here, this was just a planetary. There's a very quiescent death. It's a slow motion death. Okay. However, it could have been very different if there was a Wolf-Rayet star in the core of this, all right? Because then we would have seen emission lines coming out of it, and we would have seen, like the Crescent Nebula, we would have seen this phenomenal wind that's very powerful. The nebula wouldn't have ever been cohesive like this. It would have already been scattered. Now, over time, this material is moving away from the star, and over time, it's going to then reach a state where it's no longer being ionized, and thus won't glow, and thus it'll be lost to our eyes and lost forever until it gets incorporated into some solar system forming somewhere. If ever. So, what's this? Do you find it?
No, I'm looking at the image on screen.
Oh, I'm sorry. I thought you were looking up the pulsar.
No, I believe you.
Yeah, I'm just gonna go up to. I'm gonna do a 30-second shot, and I'm gonna go a little higher. I'm gonna go to 20,000 on this. 30 seconds to 20,000. I just want to show you one more thing about this before we move on to the next object.
Uranus.
You keep saying that. I'm going to have to show you that, man.
Show me Uranus.
I shall show you Uranus.
Uranus.
Yeah, Uranus. See, you can't say that and have it even come out with any reasonable meaning.
Yeah, it's a shame.
It doesn't work.
Let's just call it Frank.
There you go. Yes, we'll call it Frank. Where are we going, Frank? Oh, okay.
Mars, cool. Jupiter, Saturn, Frank. Neptune as well. Neptune's another beautiful planet.
Oh yeah, Neptune's beautiful. It's up now. We can look at it, I think.
Neptune is bigger than Uranus, right? Yeah.
They're roughly about the same size, but yeah, I mean, there's a slight difference.
There's a slight edge to it.
Yeah. Let's see what we got here. So this is a 20,000 ISO shot for 30 seconds of the Dumbbell Nebula. Okay, now check this out, guys. I want you to see this. Now, from out here, it doesn't. At this exposure, it almost looks like that could just be one kind of big elliptical object, doesn't it?
You're kind of vertical.
No, I know. I'm looking at it. I mean, I'm looking at it with you, but it looks like it'd be an elliptical object, right? Where the ellipse goes the long way from upper left to lower right. Okay, and then they've got that little kind of dumbbell shape in the center. Okay, now the Dumbbell Nebula. Okay, as we look at it here, that it was moving a little bit, so I apologize for that. But you'll notice that the dumbbell actually has these lobes that are, these primary red lobes seem to go here in the lower, to the lower left and the upper right. But then you got this wispier stuff in the middle on both sides. This nebula is something I wrote about today, and I did a post when I put up a bunch of photos. This is a bipolar nebula, you know, and you know, joking aside, because you could say, well, this nebula is certainly going to stay in this room tonight. Okay, the bipolar nebula is the shape. It has two polar jets that seem to have come off at the lower left there, and the slightly, you know, left and right, basically. And that is something that was discovered, and we found out that the bipolar process can only occur with stars, and this is sort of ongoing research, so this is...
Wow. You can really see that red peeking in the bottom left.
Yeah, you can.
That's exactly what I was seeing on Stellarium. Yeah. I mean, you can really see it creeping in that image you took.
Yeah. And this is actually kind of a little blurry. I mean, I sort of bumped the scope, so I really do want to take a better one. I apologize. So I'm going to do that. I'm not going to move.
That's just crazy. How? Now, what was the difference between the last image and this image that you did?
I did 30 seconds at a much higher ISO sensitivity.
Oh, okay.
And the other one was at, I'll have to look at 15 seconds at a lower ISO.
So for anybody wondering what I was looking at on Stellarium, you'll see when the image comes up. You'll see down on the bottom left of the image, you'll see it actually is red, but it's given it a purple hue because of the, you know, the mixture between red and blue.
That's right.
And it's really dark in that area, and it's showing pretty much exactly kind of image that. Cause I believe Stellarium uses Hubble images, if I'm not mistaken.
Yeah, well,
You know,
but they're color corrected, so that they're not the Hubble palette.
Right.
I actually, like I said, I wrote a little piece to actually make the Hubble palette for all these processing that I do if I want to. Now, what's the purpose of the Hubble palette? Why does it show like that? Well, here's the thing. When you take astronomical images, what you do, how'd this come out better? Let's see.
Oh, wow.
See how better, if this looks better. Oh, yeah, that's much better. Okay, when you take astronomical images, what you see is that the color of sulfur 2, which is singly ionized sulfur, the color of oxygen 3, which is doubly ionized oxygen, and the color of hydrogen alpha, which is, you know, the H2 we're talking about basically. The H2 and the sulfur 2 are really close in color. So what we do is we map the hydrogen alpha, all right, to a yellow. Yellow is green, and the sulfur to the red, and then the oxygen 3 to the blue. And that gives us the characteristic Hubble palette. So I remapped all the colors in Photoshop with a one click, so I can just click them and bam, there we go. All right. So yeah, this is kind of neat because you can actually see what you were talking about, Keith. That little red area to the bottom there. You know, that's really cool. I might be getting some dew on the corrector plate because I have to just check it because I do have some moisture on the dome. Tonight's a little wetter night than last night because last night I didn't have dew for the entire night. Let's see what I got.
Dew.
You said dew.
And Uranus.
Yeah.
Yeah, you said Uranus.
Yeah, I agree with Daryl. I think the Hubble palette is just, it's not very appealing.
Well, the Hubble palette is actually, a procedural palette that's actually used to discern details. when you look at the pillars of creation in the Hubble palette, and you look at them in the regular color, you can't see the contrast between some of the items and some of the elements. Oh, are they coming to get me?
Great.
Oh,
now
man.
you did it.
The police.
That's what you get for showing your anus.
For crying out loud. Somebody called the police.
I kill me.
Hey, that's like Alf. Ha! I kill me. Remember Alf? Alien life form?
Of course.
Yeah.
Of course. Everybody remembers Alf.
Oh, don't be so sure. There's some people that certainly don't know Alf. Oh, yeah. So, hey, let's go. Let me just see if we can do this. I don't know. It's only 10:17, but I thought we might be able to check out this object. Let's see if we can. Do you know which object I want to look for? I told you earlier.
Nope.
Yes, I did tell you earlier.
Uranus?
Wow. Man, you know, I'm not so sure. I'm not so sure I want you to do anything for me. Let me try this here. Let's see where it is. Oh. Okay.
Oh, you mentioned a couple things earlier.
Yeah, I did. I know. I'm being unfair. I'm telling just like. Okay,
So if you're saying if you're looking at a time, so it tells me it's in the eastern sky.
Yeah, it's only 12 degrees up. It's the Crab Nebula. I'm trying to. I'm just trying to hold out a little longer, but we can go check out the Pleiades.
Yeah, go ahead. Jenny mentioned it earlier. I wouldn't mind taking a peek at it. The last time I seen it was actually your first stream on here.
No way, really?
Yeah.
Wow, cool. Yeah, no, I'm very happy to show you the Pleiades. The Pleiades. We're gonna go see the Pleiades. Yeah. That's right. Here we go. Yeah. Here we go. Here we go. I'm going to be getting the hardware to actually move the dome when the telescope moves, so that the dome has always got the slit facing the telescope.
Sweet.
Yeah, well, that's very important, you know, and that way I won't ever have to move the dome anymore. You know?
How does that work? Does it put a motor, I guess, in the top tracking?
Yeah, it puts a motor on the edge of the dome, and it moves the dome in a way that.
Is it kind of like a
takes the work
a mounted wheel kind of thing?
It's actually a ratchet track. It's basically a track, a gear, and it's mounted in a geared track that goes all the way around the edge of the dome. And I'm looking right at the hole that's in the side of my dome that would actually go on the dome here to actually mount it. Now I'm probably not gonna be able to do it here in Connecticut because I think you have to permanently mount that ring to the dome, and I don't want to permanently mount things to this dome because it's gonna be taken apart.
Right.
But we'll see. I'm not sure. Not sure what I'm gonna do. You know. I mean,
Well, when you get your place out in Arizona, were you planning on getting rid of the house in Connecticut, or are you just using like Arizona as a secondary?
Well, it depends on the state of, my finances. If I can get the house out there, if I sell this house, I can buy a freaking palace out there, okay? But I only want to get something small with a couple of acres of land. The land being more important than the actual house.
Right.
And I'll have a trailer home out there for all I care, for this, you know. And then the observatory would be in a fenced area. You know, there's a couple places in Arizona I was looking at in Google Earth, and I'm just tooling around on the little side streets in Google Earth, and I come to a corner, and I have to stop and stare because I'm looking at 2 observatory domes that some guy put on his property, and it's amazing because it's like, oh, this is. I'm gonna call the guy actually. I'm gonna locate him and I'll call him and say, hi, I'm not stalking you, but I do have a question. Okay, now. Visible in the field is Alcyone at the bottom there, and Merope at the upper right, okay? Not near the top, but at the upper right. Okay, under the word time is Merope. Now, it's a little bit low still, but let's try I'm going to do a 15-second exposure.
What is it you're on right now?
This is the Pleiades.
Okay.
If you're only seeing the core stars. Okay, we see that's Alcyone down below.
Mm-hmm.
And its little retinue of followers. And then we have Merope up to the upper right. So let me do a... Yeah.
And then what's the two little ones barely coming in? Seleno? Electra?
Yeah, they might be. Seleno and Electra are actually fairly bright. So we're actually seeing a couple of field stars that actually aren't directly part of the Pleiades. Okay. So I'm doing a 15-second shot here at 25,600 ISO. Just to see if we can see the Merope band. And when we go to Maya, you'll see the Maya, the little Maya bubble.
Mm-hmm.
Let's see here. All right. I don't believe that we... Yeah, there's Alcyone at the bottom right and Merope up top. Okay, I see. Hang on. Let me zoom in on that. You see it too, I'm sure. Yeah. Can you see the you see that band of, you can see that harsh sharp edge?
Mm-hmm.
Yeah, that's not an artifact. That's actually the reflection nebula.
Huh.
Yeah. And then because it looks unreal, you know, when you see it, you know, like this on a telescope. Then if we go, let's just jump up to Maya here if I can figure out which way to go to Maya. I think we got to go this way. Okay, and maybe this way. I don't know. I don't know. I'm lost in the Pleiades. I'm too zoomed in. I'm too, you know. Let's do another 15 seconds at 25,600 ISO to see what we got. I'm getting just.
So you couldn't zoom out a little bit and take it?
No, I'm prime focus.
Oh, okay.
Yeah. Now, if I took the time, we could actually mount the camera with the telephoto on the mount I have, but I have that set up for a aerial anomaly equipment, so I can't change it out without some time being invested. But it's okay. You know, if you come up here tonight, you just come on up, you know.
Sure. I'll be there in 3 hours.
Yeah, 3 hours.
4 hours.
That's hoofing it, too.
Yeah, right?
Yeah, okay, I didn't see it there.
Not if I take the official P&K helicopter.
Ooh, wow, that would be cool. Wow. Yeah, I don't see it. Yeah, the Pleiades, I wish that I could show you the whole Pleiades. I mean, I might be able to here, actually, if I just... Okay, there's Alcyone down there. And Alcyone is actually... Yeah, so I really have to go this way. And this way. Other way. My other left. Okay, so that's Alcyone and Merope.
Yep.
Yeah, and if we go up and then over, other left. Now we come to Maya, and there's Maya and Solano.
And Maya's the one with the little bubble, right?
I believe that Maya is the one with the bubble. We're going to catch that now if we can. So 15 seconds, 25,600. Like I said, it's still a little bit in the murkiness, so we'll do our best here. So I hope you guys are enjoying this. It's a nice casual night at SkyTour LiveStream.
Absolutely beautiful crowd in chat, as always.
Yeah, they're good people. You know that? I wouldn't do it if it wasn't for them, to be honest. I mean, I wouldn't do it just to do it. I do it because these guys, you know, appreciate it. That really drives me. I like that. I mean, I'm passionate about it, but you know. Okay, what did I miss here? What did I miss? No, gosh darn you! I hate when you do that. Okay, I think I see it, but.
Mm-hmm.
No, I don't see it. Did I get the wrong thing here?
Well, it looks like. 1, 2. So that's Electra. No, that's not it.
These are the stars here that we're looking at.
Yeah.
And those are. If I got this right, we're looking at. Oh, wait a minute. That's not right either. Then.
Yeah.
Okay, that's. I'm expecting that to be. That's actually. I think that's actually Taygeta on the right. And on the left is Asterope.
Well, if it was
and Maya's, if that's Asterope, then Maya's down here.
Yeah.
Is that Maya? Yeah, I see.
Maya is like straight, north of north, straight up from Alcyone. So.
Yeah, well, it is, and that's actually right on the northern thing. So I should, if I do this, if I go like this, I should come straight down and see Alcyone down here at the bottom. Okay, we should see it now, coming up, anytime now. Yeah, see, we don't. It's not there, so I got the wrong thing, obviously. Oh, I'm sorry, I was going the wrong way. My mistake. I'm mistaken, sorry.
Mr. Astronomer.
No, I was actually just, I wasn't doing the right thing. I was moving us the wrong way. You know, because the telescope's on a weird angle, so it makes it goes like, it does the wrong maneuvering.
If anybody wants to get Mark a present for Christmas, he is accepting pairs of electric heated long johns.
Oh, well, let me tell you, I gotta. There's Alcyone. I have to be really careful about getting so freaking cold. I'll tell you that, because I forget. Like today, I was planning my observing session all day. Well, partly during the day. I had to do some real work too, and I actually forgot to eat today. I was like, oh, why am I like got a headache? Oh,
don't you hate when that happens?
Yeah, I was supposed to eat. You know, I think I was supposed to eat. Oh, okay, that's what happened. Yes, indeed, and I didn't eat. So I was like, oh, well, you suck. Okay. Okay, so let me take this up here. I go this way, and now we should be able to go this way.
Ever so slightly.
Yep. And now, if I go over this way, and then this way, I know, right? It's like we're playing like it's like chasing mice on the screen. Okay. All right. This I believe. This is new. Okay. This is now. Okay. Now we are looking at. I believe that's Maya. And okay, that star doesn't belong there. Let's take a picture and see what I see.
Yeah, I was gonna say if I had to guess, it'd be like Maya and Asterope and Taygeta, and but I'm not sure. See, I'm not used to viewing it this zoomed.
I know that's
what throws me off.
Well, plus it's on an angle, and it's kind of on a weird, stupid angle, which is problematic. But I'm not going to waste a lot more time on this. I want to actually see if we can see some really cool things. Like I want to see if I can see the Crab Nebula.
Crab people.
Oh, you definitely have some. Oh wait, hold it. Hold it. Oh great, yeah, they're going to do that to me too. Just when I thought I saw it. Okay, hold on. Okay, see, you can see right there, that star on the right, that's actually Maya. Because you can actually see the little hooded bubble on it. See it?
Mm-hmm.
Yeah, that's it. Okay, so we did get it.
There you go, people.
There you are, and they didn't even ask. we didn't want to see that. I mean, we're just whatever, you know. All right, I'm gonna say go to, and we're going to the other thing here.
To the Crab Nebula, Batman.
To the crab! To the crab! To the crab! To the crab! Ooh, that's actually visible. So let's see what we got. It's actually it's low and in the murk, but we'll do our best.
You must have very good viewing skies out there tonight, because you said this was in the murk and this didn't look half bad.
Yeah, it's in the murk. Yeah. Well, M1 is in the murk, and by murk I mean there's a little light pollution down there that's problematic, and I just can't stand light pollution. What can I say? All right, now let me see if I can do a acquisition with the 4K guy here. Let's see if it'll show. I can't see it. Let me, if I move the scope a little.
By the way, I did post that you were live on the Facebook pages.
Cool, thank you.
I actually put it on all three of them. I put it on Astro Imaging Live, and then SkyTour LiveStream, and then of course P&K page as well.
Oh, thanks, Keith. That's nice. You are very good.
Very good.
Yeah, thank you. Very good, thank you. I am very happy that you are willing to be doing this. All right, so let's just try 32,000 for 15 seconds. It's going to be bright. Too bright probably, but I just want to just see what I got. I think I saw it there off center, but I could be wrong.
Well, look at Jenny's new sassy profile picture.
Oh, I can't see it.
You have to look on Facebook.
Oh, man.
Good one, Jenny. As always.
Yes, sirree. We're only 12 degrees above the horizon here, so it's gonna definitely.
You know, I don't blame you there either, because when the moon's coming up, me and Paul hate that as well.
Yeah.
But we are viewing something a lot more local, so it gives us the weeble wobble.
Yeah. Okay, I don't see it in the view here, but that's okay. I know what I should be looking for, but I don't see it there. It's not visible there. It's too low in the murk. In fact, I can't even see. None of the stars of Orion are even visible right now. It's funny. At this time last night, I had some of Orion's stars. Maybe not. Yeah, I would have to wait a while to try the crab again.
Good night, Jenny. If you are leaving, have a wonderful night.
Well, she's just sick of it. She wants to get out of here. It's like, tell me to get off this stupid thing. It's like so dumb.
I think she was enjoying the Fiat.
Yeah. Yeah, we did that just for her.
And now we are also joined by Mr. David Schmidt.
Hey,
in the
David.
chat now.
Yeah. Yep. And David, I did talk about electron degeneracy pressure again, which you and I had a little bit of a discussion about because you were interested in what that term was, and I couldn't remember what it was, and it was actually, as you pointed out later, electron degeneracy pressure. It was that in the discussion of the black holes and the white dwarfs. Let's see, NGC 246, is that what it was? Oh, yeah.
Man, you got tons of sirens up that way, huh?
Yeah, I know. I gotta keep trying to avoid the police here. Okay, obviously just kidding. I hope I'm kidding. Okay, now let's see if that will show up. Where are we looking there? Oh, okay, that's going to be almost in the south. And it's going to be at 34 degrees above the horizon. So we can try this, see if we can see it. Moving.
Gotta put a muffler on that thing.
Oh, it's just that the sound comes through pretty loud. It's moving quite a bit of weight, you know.
Well, that and you are in a dome.
Yes, and all the sound comes right back to you.
Yep.
All the sound comes right back to me. Okay, 15 seconds at 32,000. I'm just going to go for it and see what I got. I'm looking for NGC 246, which is a planetary called the Skull.
The skull.
Yes. Let's see if we can see the skull.
Did Amanda ever message you?
I don't know.
Oh.
I don't know. Let me find out right now. Nope. Oh, hey, how about that? Look at that.
Oh, shooting star.
Nope, not a shooting star.
What was it, plane?
No, satellite.
Oh.
And the skull. Here, I'll show you. Okay, oops, not that. Just on here, watch this. Okay, there's a skull. And right next to it is a satellite going through. Now, just the length of this trail, you can figure out where that satellite is. And the reason is because when you look at the exposure time, it was 15 seconds, all right? Never mind the sensitivity, that doesn't matter. 15 seconds. It went 15 seconds across that much sky. Now, knowing the size of the skull, which we see right next to it, we can figure out how many skulls widths it went. And based on that, we can convert that to an actual linear distance in space. Okay? It takes a little, doing, because you have to know how fast orbital speeds are at different orbits out there. But then you can get the exact height of the orbit that would make a trail that's that long for 15 seconds. It's pretty cool.
So that's your tricks, huh?
Girl, such a big trail. It's it's typical deduction, See, we get satellites. I like that. I like when we do this stuff.
I actually should have set my stellarium up to your town. I would have seen that satellite coming over.
Actually, you probably would have, in fact.
Yep.
Yep.
Stellarium's been pretty good with their satellite data.
Yeah, I've noticed that they actually have some pretty good ones, that come out pretty cool. One thing that I like is GoSat Watch. Now, I have Stellarium on the iPhone, I have it on the iPad. I also have GoSat Watch on the iPad and the iPhone. And GoSat Watch is more complete because all it does is satellites. And it knows exactly where satellites are at every single turn, which is really cool.
What time are you going to go till tonight, Mark?
I'm probably going to be going just a little bit longer, not much longer.
Okay, I was going to say I have to duck out around 11 because I do have to get up at 5 a.m. tomorrow.
Okay.
Just so you know.
That's fair.
You don't have to stop for me by any means. I'll just...
No, but I'm going to be going, because I went 5 and some odd hours last night, and so tonight I wanted to give myself a little bit of a break and not do that kind of time.
Hard time.
That's hard time, all right, dude. That's like real hard. Yeah, real. Yeah, right. It's like that goddamn internet thing. It's like the damn internet thing.
The interwebs.
Yeah. Yeah. Yeah, Amanda never got back to me, so she's definitely down for the count. Probably sleeping.
Yeah.
Probably won't get up until midnight, and be up until 10 a.m. tomorrow, or 1 p.m. or 2 p.m. and then go back to bed.
Yeah, it does kind of seem like that. We have her and then she'll disappear for a couple days. And then she'll be back.
Yeah.
2-3 days.
Yeah, I have no problem with that. I just want to, make sure that she's doing okay, because, she helps me greatly.
Absolutely.
Right. Hey, I still got to send you your crater, man. I can't believe it. It's in the box sitting on my shipping table still.
Son of a... Well, I'm telling you, throw Aristarchus Plateau in there while you're at it. Or Clavius.
Yeah, I haven't printed out Clavius yet. I gotta actually do that.
Oh.
Clavius would be a good one to do.
Well, Aristarchus Plateau. I'll take that in a 11 by 11.
11 by 11. Wow.
Well, it's a pretty big area.
Yeah, I mean, I'll have to buy a whole another roll of material too.
I'll send some to you. How much is that?
Oh, it's like $49 for a roll of ABS, and you might blow through a full tenth of the roll doing that.
No problem.
Well, actually, it depends how thick you make it and what the vertical. Oh, look, comets! I moved the telescope by accident.
I was going to say, that's a lot of comets.
Yeah, right. Yeah, I moved the telescope by accident. Sorry.
Did you accidentally bump it just a tad?
Just a tad. It's okay. Nobody minds. You know, actually, this was a technique we actually used. Okay, see, there's the skull. Right, it's there. It's the blurry thing right there. We actually.
Oh, you know, I gotta tell you about a dream I had too. For some reason, I had the studio built, the new studio built, and we had a shelf in there.
Yeah.
That had a whole bunch of like little cubbies in it, and each one of those cubbies were filled with 3D printed craters.
Oh.
Like you had like the Clavius cubby, and then you had and it was basically anybody that wanted one, we would just pull them out of there, pop them in an envelope, and mail them.
Well, that's
crazy.
That's effectively what I'm doing, though.
Oh,
well,
there you go.
Because I have
psychic.
Yeah, well, and actually the craters we're making molds of the original craters off of the 3D printer after they've been finished to the point where they're just beautiful.
I tell you what, you get the molds and you make the molds, and then you send them down to me, and I'll handle the paint.
Do you know how to use the airbrush?
I'll figure it out.
Okay.
Craters are pink, right? Hot pink?
Yeah, you know what? I'll have the FX Models Planetary Replica Division out in Colorado do that part.
You're going to send them all the way out to Colorado?
Oh, yeah. They're going to distribute them from there.
Son of a bee.
Well, no, that's good. I mean, they're the right people to do it. You know, they've got it all down. So this is that little tiny skull, which has almost no resemblance to a skull. So,
somewhat.
Kind of disappointing. Maybe if I took like 20 shots of it and did a
stack them.
Processing, stacked and processed, you might actually see something, but it has to be something more spectacular than that, don't you think?
Well, you can kind of see it.
It's low surface brightness, yeah. You can. You know, you can.
I'll tell you this, I can see it better on my computer monitor than I can the extension screen. Like, I can see it better because I have YouTube feed on my computer monitor, and I can see it better there.
Interesting. I suspect that's
Well, we are getting a lot of interference with the camera too on that. The lines are jumping up and down the screen there.
What?
We're getting horizontal lines.
Where?
That just keep appearing. It's almost like it's a bad connection somewhere.
Wait, here?
It has to be from there because I'm seeing it on YouTube as well.
I don't see anything on my screen at all. And I'm seeing what the camera's outputting before you actually get to see it.
Yeah, I mean, you wouldn't even notice it if you weren't looking for it. I just see it on this screen here. I mean, you can barely see it on YouTube. Barely.
Wow. Okay, I don't see it at all. Personally, I think you're causing it.
Probably. Never know.
Hey, look. No time of the night looking at the night sky is complete without going to something else that I know you'd like to see.
Uranus.
My God, man. That's funny. Let's see here. Did you ever notice that Uranus is actually kind of a sky blue color?
Yeah.
And when you look at it in the telescope, it can actually just look white. You know?
More like an alabaster.
Who you calling a bastard?
Hey, simmer.
Okay, so that's southeast. Okay, good. So let me go there. I'm almost there, as a matter of fact. Here we go.
There we go.
see what we got here. Oh, yeah. Okay. Let's go see. So maybe that's what we're looking at. Yeah, okay. Okay, so that little faint object right there in the center, not the brighter thing down below, that's Uranus.
Ha! Zing!
So now will you be quiet about Uranus?
It's been years since I've seen Uranus.
Oh, it's like been forever since I've seen yours, huh? But there it is.
There she be.
Yep.
In all her glory.
Yep. Let me just take a photo so we can actually see if we can see the umbriel. Let's just do this. 20 seconds at not 16,000. That's ridiculous. Let's do it at let's do 8,000 20 seconds, just to get a good feel for what we're looking at in the sky there. Get a good flavor for the star systems nearby. Okay. You know, yesterday we looked at Aldebaran, and you know, people were used to thinking of Aldebaran as a fairly, you know, big star, but then you compare it to stars like Antares, and it's like, yeah, sorry, Aldebaran's a piker when it comes to this. You know. All right, so here comes Uranus. There we go. So here we go. Now let's zoom in on Uranus here. There we go. Look at that.
There we are.
There it is. Then you can see in the outer glow, you can see, and you can actually see one of the moons just to the upper left there.
Mm-hmm.
Very, very faintly. And let me see what moon that is.
Actually, there might be another moon way out there.
Yeah, that's the...
Actually, 1, 2, I see 3.
Yeah, you could see Umbriel, which is up above, and a little bit to the right is Titania.
Mm-hmm. Actually, that makes 4 then. No, 1, 2, 3, 4. I got 5.
Really?
Yeah, I told you. Super screen.
Oh,
Very little. Like each one of those ones is probably a pixel each, if that.
Oh, I actually see those here when I get up close to my screen. And people, you know, if I turn on my light, you can see where I am. Hi, guys.
Yeah, there's one just off to the right, and then you have 1, 2 to the left there, and another one.
Umbriel's pretty bright.
And there's one way out.
Yeah, if that's actually a moon.
I think it is.
Because we got Miranda is below. Ariel is further below and to the right a little bit. And then we have Umbriel above and Titania above and to the right. So there's 4 visible.
1, 2, 3, 4.
2 below, 2 above.
So maybe that one
Actually,
isn't.
you know what? Let's do this. I'll do this again.
It could be, though.
I'm going to do something else. I'm going to do something here because we took this picture, okay, and what we did was we actually went at 20 seconds. Let's go down to 8 seconds and shrink the size of Uranus so that we can actually see more of what's around it. And hopefully the ISO will still allow us to see the moons. You know what I mean?
Soon to find out.
Yes. I mean, they were faint as it is. They probably needed this, but I did notice that we can actually catch this detail sometimes. I'll get rid of that. Let's go here, and go out there, and go there, and now zoom in. Is that any help?
Not really.
Maybe I was looking at the same one. Maybe I didn't actually change the picture yet. Hold on. Oh no, that was the picture. This is less. Okay, so now Let's drop down to 4 seconds at 8,000. We're going to rapidly get down to the point where we can't see the moons anymore because they're not bright enough. Let's see.
Might be able to overexpose Uranus, and then the moons might pop.
Yeah, but then Uranus is going to be too big, too bloated. Yeah, now we can't see the moons at all. Oh well, I tried.
Oh, shucks.
Yep, that's right. But it's Uranus, guys. This is Uranus. Thank you very much, Uranus, for, yeah.
I want to thank Uranus for coming along. Thank you, Uranus. Thank you very much. Yeah, yeah.
Once again, a beautiful planet with an unfortunate name.
With a name that needs to change. Welcome to planet Frank. This is the planet Bob.
Frank.
Actually, I'm glad we looked at Uranus for the amount of time that we did because I want to now check out Neptune.
Neptune.
And I want you to notice the color difference. Hey, come back. Come back. There you go. Good girl. Coming back. That's good. Okay. So now we just go up and bring it over. Alright. And now let's just zoom in right now and just check out. Okay, look at the difference in the color with Neptune versus Uranus. Uranus almost look kind of white. Neptune's clearly blue. Very, very clearly blue. Let's do, I'm getting dew on the lens here on the corrector plate. Let's go do, before I lose it entirely, let's do 10 seconds at 8,000 just to try and catch this. Let's see if we can see Triton, which is above it. Nereid is actually quite a distance away. To the left. Let's go see. Let's go see.
Processing.
Processing. Doot, doot, doot. All right, here we go. All right, look at that. Well, there's Triton, obviously, right above it. And there's Nereid off to the left. And I'm noticing that I don't like the focus. I don't know what happened there. Let's just go back for a second. And let me just pop in to a higher focus zone here and see if I can improve this. 1 second, please. Just a minute.
Holding.
Dave, I'm afraid that the Earth-facing antenna stands a 14% chance of failure in the next 30 minutes. Screw you, Hal. I'm sorry, Dave. I'm afraid I can't do that. Alright, so now let's do another 10-second shot at 8,000. The other thing that happens is because, you know, as you move in a dome, your body is, you know, carrying heat around with it. And if you turn a certain way, maybe you release a little thermal poof, which goes through the dome slit, and it can affect the viewing very badly. And I was saying yesterday, what I need is a system by which we can actually have a the dome heated, seal it. Okay, that's better. Look at Neptune there, Nereid off there to the left rather. There it is. That's the Uranus system. I'm sorry, Neptune. That's it. That's the farthest planet in our known and agreed upon solar system, folks. Right there. That's the last planet.
That's the farthest one out there.
Neptune. Yeah, and beyond it is the very cold and very demoted Pluto.
And how many AU is that away?
Well, about 30.
30.
Yeah. The actual distance is let's see, 4,371 million kilometers.
Mm-mm.
Yeah, I did that in my head. So it could be wrong. Yeah, 29.2 AU, actually. So 30 AU. And beyond 30 AU to 50 AU is the Kuiper Belt, within which Pluto is now defined to be within. But it's a really pretty shot, isn't it?
Mm-hmm.
Neptune with its retinue of moons. Not bad. Not bad at all.
Not too shabby.
No.
And I'll tell you what, this is where I leave you for tonight.
Okay, well that's okay because I am getting due on my lens and I'm going to actually have to shut down. I don't want to, but tonight is different from the other night. The other night was just, last night was gorgeous. I was up almost all night actually, and I didn't get any dew. And tonight I've got it dripping. So
it's just one of those things.
Yeah, the optics has to be pre-judged.
Hashtag astronomer problems.
Yeah, right. Wow.
But once again, thanks Mark for having me on, and to everybody in the chat.
And thank you for coming on, man. I
Moon
really
stream
appreciate
should
it.
start probably this weekend at some point. We're hoping.
Okay.
So, and hopefully you'll be on as well. So, and hopefully Bill will be on as well because the peak is. I believe Bill said that he will be with the camera out because the peak is the 20th.
Yeah.
So hopefully while he's producing KGRA, he will be able to have the camera out as well. But I'm not sure. But I'm pretty sure you'll get some in, and I think P&K will start back up this weekend at some point. So.
Well, I'm thinking actually I might do a meteor stream as well, and mount my camera on the back of the telescope so that it's always tracking the same area, and then we can move it around.
Oh, there you go.
Yeah, and I can actually move the telescope around from in the house. I don't even actually be out here. I can just use the Wi-Fi, go through the Wi-Fi, and control the telescope from inside.
Sweet.
So, and I might just have to make sure that I don't move it too far so that the dome doesn't obscure. But again, once I have that dome system, then I'm gonna that's gonna be totally a non-problem again. You know.
Mm-hmm.
Yes, sirree.
Absolutely.
And the observatory maker is actually interested in a product I have to keep the I've designed to actually keep the dome from bouncing as it rolls across these roller wheels, because as it reaches the seams between the domes, it goes between the dome segments. It goes boom, 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 and if it stops on one, then every time the motor is forced to torque out of that little well that it's in, that's wear and tear on the motor. So it could make it a lot easier if we do something to bridge the gap, basically. So I've designed a little bridge the gap piece. And all you need is like 10 of them, put them on, and bam. And you could probably use double stick tape to do it, But
there you go.
Once you get your dome in place, I would just epoxy them in. That's really how you do it.
Yeah.
Yeah,
Super glue.
Yeah, well, super glue would actually work, actually. Yeah.
Yeah, super glue is great.
It is. It doesn't handle shock too well. But
no.
Yeah. So I won't electrocute it. Anyway.
Very good.
Hey, folks, I want to thank you. I want to thank you, Keith, for coming on board. Thank you.
No problem.
Thanks for joining me on this stream tonight. And we're going to call it a night here. And I'm leaving you with the Crescent Nebula, which is that wonderful Wolf-Rayet star illuminated nebula. It's both an emission nebula and a planetary nebula. So thanks, guys. I will see you again. And just keep looking up, huh? And we'll see you soon.
See you later, everybody.
Good night, folks.